So a molecule is basically anything that is covalently bonded. And if you guys want to familiarize yourself with that, I have done a video on bonding. So like I said, molecules are anything that are joined together by a covalent bond. So that means you have one molecule here and another molecule here, and they are joined together by a covalent bond. This is obviously a generalization of what a bond is, but more or less that's how it is. A lot of the times, like in the textbooks, I'll show it like this. Like if you have this little pink element, you have one here, and you have another one right there. That's another way to show bonding. You can also have bonding that occurs between two different molecules, still a covalent bond. So it would look like this. Alright? Maybe the pink one's a little smaller. So the difference between these two types of molecules is that in this case, both atoms involved in the bonding are the same. Right? And in this case, they're different. Now they're both covalently bonded, and remember, covalently bonded means you have atoms with very close electronegativities. It's mostly nonmetals. So here we have two atoms that are the same, being covalently bonded, and that is called a homonuclear. And since there's two of them, we call it a diatomic molecule. And in this case, since we have two different atoms, we call this a heteronuclear diatomic molecule. Now, both of these types of molecules are very important because this type of molecule is going to teach you how to start naming your diatomic molecules in the first place. I'm going to do that just a bit later. I'm going to focus on this one first. These are your homonuclear diatomic molecules, and the reason I want to go over them very quickly is because there are several that are always found as diatomic molecules in nature, and I want to go over this right now because there's actually a really funny acronym to remember them all. So what I'm going to do right here is just go over the homonuclear diatomic molecules. So the acronym that I learned is actually Brinkelhoff. It's going to make sense in just a second. So this is my acronym. So you have BR, I, N, Cl, H, O, F. So your diatomic molecules are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Now what this means is that if you look at a molecule of bromine, it's going to be Br2. This is because in nature it exists as a diatomic molecule. The same goes for iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So these are your homonuclear diatomic molecules. Okay? Now moving on to our heteronuclear molecules. Diatomic molecules, sorry. Now, these are still obviously diatomic molecules, but they just have different atoms in them. An example is HCl, right? These are two different atoms, so these are diatomic molecules. And these are the molecules basically that are going to help you to start naming compounds. Now there is a third type of molecule called polyatomic, and I'm sure you can guess what that means. Right? That just means, say I have like a central atom right here, Whereas a diatomic would have only 2 atoms participating. A polyatomic, sorry, different color. Polyatomic would have more than 2. So in this case, we have the bonding of 4 different atoms, right? So this is your polyatomic ion. I'm sorry. So this is your polyatomic molecule right here. So now we're going to move on to starting to name some of the structures. So now I want to quickly talk about different types of molecular formulas. You'll kind of pick this up as you go along in your chem course, but it's just good to kind of brush up on it right now. So there are a couple of types of different formulas. The best way to, I guess, exemplify it would be to look at a specific example. So what I'm going to do is go with H2O, okay? So generally in your textbook, different atoms will have different colors like already pre-assigned to them, and in this case they're given oxygen, the red color, and they're giving hydrogen, the white color, right? And then it's obviously covalently bonded. Now this is one type of chemical formula, okay? What this is the structural formula. Okay? Now, the reason this is a structural formula, if you think about it, is because it actually shows you the structure in which the hydrogen and the oxygen are connected. See, it's not linear, it's a bent shape. That actually shows you some kind of connectivity. Another way to show a structural formula would be to just take the oxygen and then have the little hydrogens attached right there. This is also a structural formula because it shows your oxygen and the orientation of your hydrogens. The difference between these is simply that this one shows your bonds as lines, and it can also be called a ball and stick model, and the reason it's called that is because usually if you get like one of those chemistry sets and you were to make H2O, it would look like this. You would have the 3 balls and the stick, like the sticks basically here to show you the bonds. So these are structural formulas, and they show you what elements are involved and the arrangement, okay? Now, on the other hand, what you have is a chemical formula. And the chemical formula, so the chemical formula shows you only the composition. So what does that mean? That means it's going to show you only what the molecule is composed of. So in this case, if we were looking at this ball and stick model and you were told to give the chemical formula, you would say, well, I have 2 H's and 1 O, so your chemical formula is H2O. So I hope that's clear on what the difference is between the chemical formula and a structural formula, but let's just do an example right now. Okay, so let's do an example. Like I said, certain colors are denoted already in the textbook to refer to certain atoms, like red is oxygen. So I'm going to write that right there. Red is oxygen. Sorry if that's really dark. I'll make it brighter. Red is oxygen, and then white is hydrogen. Okay? And generally speaking, what you have is like a dark grayish, blackish color. And I'm going to make it light grayish, is carbon. So I'm going to denote it right here. So we have carbon. And in this example, all I need to do is carbon, oxygen, and hydrogen. So I'm going to go ahead and make this example. So a question they can give you is as follows. They'll give you some kind of formula. So let's say I have an oxygen right there. I have a gray atom and another gray atom. Right? And then I have some white atoms. There. There. And I'm going to make the gray a little darker, just so I don't want you guys to get confused with the white. Oh, that was supposed to be white. Okay, I hope that is a little clear. And I'm going to make the bonds in like a tealish color just to kind of show. Alright, so here's my bond right here. Little bond right here. There. There. And there. Okay? Now, like I said before, we have the gray as the carbon, and we know from earlier that the oxygen is the red, so we have an oxygen right here, and all the whites are hydrogens. Now, just to review a concept from before, we know that oxygen is a divalent atom, which means it can make up to 2 bonds. So as you can see, that's illustrated right here by the fact that our oxygen, which is our red molecule, has only 2 bonds. And then we know that carbon is tetravalent, which means it can make 4 bonds. So we have 4 bonds right here and 4 bonds right here. So first question would be, what kind of formula is this? And, well, you have 2 choices. You have your structural or your chemical formula, right? Well, let's look at it. In this case, we can actually see how the atoms are arranged, right? So if you said structural formula, you are correct. So now, after that, they'll ask, give the chemical formula for this structural formula. And this is how you would do it. You would count up how many atoms you have of everything. So let's start with the carbon. We have 2 carbons. We have 2 carbons. We have 1, 2, 3, 4, 5, 6 hydrogens. And 1 O, right? And once we have that, you just write it out. We have carbon 2, H6, and an O. So I hope this makes sense, but I'm going to take this actually one step further right now. It's pretty common to have a structural formula like this and a chemical formula kind of both give an essence of what the structure is going to look like. And what I mean by that is over here we have written C2H6O, right? Now, think about it if I wrote it like this, C2H5OH. Now, do you see why this one is a little more accurate in explaining this molecule? Because in this case, if we were to draw it out, if I just follow this one, I would say I have C2, right? And then H6. I would just kind of start making my H's around it, just kind of arbitrarily, because I know it's C2H6. But now where does my oxygen go, right? But if you look at the bottom one, I would go with C2, and then I know that I have H5, 2, 3, 4, 5, and this leaves my space open for the oxygen to come right here, and then now my space for my hydrogen, my 6 hydrogen, is right there. And then if you just do the bonds in like that, I hope that kind of makes a little more sense. And you can see that this molecule are the same molecules. This is just a little more accurate of the way it's shaped. But I hope you get the point of C2H5OH. And if you're curious, this is called ethanol. Don't worry about that, I'm going to get to the naming just right now, actually.